In this video, we're going to look at how we use the normal distribution to conduct difference of means testing. In particular, we're going to look at one sample difference of means tests, where we're comparing the mean of a single sample, we'll call that mean our statistic, against the mean from a population, which we'll refer to as our population parameter. The general intuition behind one sample difference of means testing is to examine the degree that our observed mean, that is our sample statistic, was randomly drawn from a known distribution that contains our population mean or our population parameter. The two options are that we are reserving a difference of means between our sample statistic and the population parameter, one, by statistical random chance, or two, because the sample represents a different population than what we're assuming is the population mean. Let's take a look at how both of these play out in illustrations now.
So our one sample of difference of means test begins with a null and alternative hypothesis. For the null hypothesis, we would state that the sample mean, which we noted here as x bar, is equivalent to the population parameter mu. Or you can state the null hypothesis as the difference of means, that is x bar minus mu, would be 0. The alternative hypothesis is, of course, the converse of the null hypothesis, so here we could write that x bar is not equal to mu, or x bar minus mu is not equal to 0. Given then that we can characterize the null and alternative hypotheses about being about 0, that is, the null hypothesis says the difference between x bar and mu is 0, whereas the alternative hypothesis says the difference between x bar and mu is not equal to 0, then the standard normal distribution can characterize a difference of means test for both of these hypotheses. That is, in a standard normal distribution, we know that most of the observations should be 0. That is, if the null hypothesis were true, we know then that the difference of means between our sample statistic x bar and mu should be 0 most of the time. What we're really asking then is whether or not the sample statistic x bar is so different from mu that the difference of means is unlikely to have been generated by a distribution where we should find 0 most of the time. That distribution, of course, is the standard normal distribution. Keep in mind here that we're approximately looking for a difference of means when converted to the standard normal to be either less than 2 standard deviations from the mean of 0 or greater than 2 standard deviations from 0 to be significant at the 95% confidence level. Okay, so let's take a look at an example. Suppose we sample 646 schools in Pennsylvania that gave the SAT scores, and the average SAT scores for those school districts was 966 with a standard deviation of 109. In this case, we would have x bar equal to 966 and sigma equal to 109 with n equal to 646. Let's further suppose that we know that for all students that took the SATs in the United States, there was a score of 1059. So we'd say that the mean we want to compare our 966 to is a mu value of 1059. Note here that I don't have a standard deviation for the population, and I don't really need one to conduct a one sample difference of means test. The statistic we want to use here for a one sample difference of means test is called the t-score, or t. The formula for t is given as x bar minus mu in the numerator, so we're going to subtract our population mean from our sample mean, and we're going to divide that by sigma, the standard error from our sample, divided by the square root of n. You'll note here that a t-score looks very similar to a z-score. The only real difference between a t-score and a z-score is that we're conditioning or weighting sigma, our standard deviation from our sample, by the size of our sample. We didn't need to do this with a z-score because we were dealing with a population rather than a sample. You'll also note here that when we're doing our test, we're using a t-distribution rather than a z-distribution, although at a high sample number, that is when n is significantly large, the t-distribution converges with the z-distribution, or the standard normal distribution. Really, the only differences you get between t and z are when sample size is small, and when we say small, we mean generally less than 30. So functionally, t-scores and z-scores are almost equivalent, except for the fact that we're going to condition or weight the standard deviation by sample size. So if we plug in our values for x bar, mu, sigma, and n, we get t is equal to 966 minus 1059 in the numerator, divided by 109, divided by the square root of 646. If we reduce this down, we get t is equal to negative 94, that is our difference of means in the numerator, divided by a weighted standard deviation of 4.29. In other words, what we're really asking with t is the difference of means, that is what's in our numerator, a lot greater in magnitude than the variation we have in our data. So we call that denominator the standard error of the mean, which is giving us the variation around that difference. So you can see here that our t-score is negative 21.9. Just by eyeballing our students' t-distribution, we know that this is going to be statistically significant because we really need to get past the -2 or +2 standard deviation marks to be at the 95% confidence level. Of course, if we want to know more precisely what we should be looking for, we can use a students' t-distribution table and find our significance level and comparing our critical value against what we have from our analysis. So if we want to be really confident in our statistical inference to see if we should reject or fail to reject the null hypothesis, we can refer to a t-distribution table, which is very much like the chi-squared tables we looked at in our previous videos. So here I have a t-distribution table, and you'll notice that just like our chi-squared table, we have our confidence level on the columns. That is, they're listed across the first row. And we have, once again, degrees of freedom listed down that first column, which characterize each row. For a one-sample difference of means test, this degrees of freedom generally refers to sample size. So we calculate degrees of freedom as the number of observations minus 1. So in our case, we had 646 observations, so we subtract 1. We have 645 degrees of freedom. Now you'll notice here that the degrees of freedom don't go to 645. It doesn't really go past 30 because, as we saw with our illustration of the student's t-distribution, the results generally converge at a n greater than 30 with the z-distribution or the standard normal. So we're going to use that final row to look up our critical value of t to test our value that we've gotten from our sample and draw a conclusion about our null hypothesis. So you can also see that at the bottom of our table, we have the confidence level. We're looking for the 95% confidence level, and that gives us a z-score of 1.95996, which of course is not surprising if we said that the 95% confidence level is associated with the 2 standard deviation mark on the standard normal distribution. Now, we're comparing our negative 21.9 to that 1.96, keeping in mind that the t-distribution and z-distribution are symmetrical. So if we have a negative value, we simply put a negative sign on our z-score or our t-score, and that allows us to make that comparison. So since negative 21.9 is less than our critical value of negative 1.96, we would then have a confidence level of 95% to reject the null hypothesis and conclude that students in Pennsylvania schools tend to perform differently on average than students in the nation. And in this case, we find that students in Pennsylvania actually perform worse on the SAT scores on average than students in the rest of the country. So that wraps up our discussion of one-sample difference of means tests. Once again, these tests are useful if you already know the population mean. If you don't know the population mean, then you can't obviously do a one-sample difference of means test. And we'll take a look at how we can then do independent sample difference of means tests, which in some cases are more useful, to compare the means of 2 different groups you've collected data on.